So that was how to encrypt using RSA. Let's now see how to decrypt. As I said, this is public key cryptography. So you announce your N and E number for everybody to hear. So that essentially means you are announcing to everybody, if you want to send data to me, encrypt that data using this N and this E via RSA. So you're announcing how to encrypt for you, but obviously you do not announce how to decrypt. And now we are going to see why it would be difficult for someone that has N and E to actually decrypt your message. So let's see. First of all, we know that the number E is co-prime to the number P minus 1 times Q minus 1. This is one of the rules of RSA. The multiplicative inverse of E modulo P minus 1 Q minus 1 exists because they are co-prime. This is guaranteed. We have seen this earlier. This means there exists a D number such that D times E is congruent to 1 modulo P minus 1 Q minus 1. Okay, so this is based on the lemma we have seen earlier. This means there is an integer k such that D times E is actually equal to 1 plus k times P minus 1 Q minus 1. Therefore, take the code word C, the encrypted data, C to C, and raise it to power D, this D value, the multiplicative inverse of E in modulo P minus 1 Q minus 1. So raise C to the power D. Essentially what you get is M to power E to the power D under modulo N, because you see that's how we computed C. C is essentially M to power E modulo N. Therefore, just plug that in, you get M to power E times D. But E times D, as we have seen, is equal to this for some k value. And k itself is not important here, but there is such an integer. Now, at this point, we will assume M and P, and also M, and this should be Q, are co-prime, which almost always holds. And you can ensure this with some tricks that I will not go into. So this is not, let's say, a weakness of RSA. Let's say you can ensure that this is the case. But here, let's assume this holds, which you can make sure. In this case, we can just apply Fermat's Little theorem to write M to power P minus 1 is congruent to 1 modulo P, and also M to power Q minus 1 is congruent to 1 modulo Q. And therefore, when you raise C to power D, you see this is equal to M to power 1 plus K times P minus 1 Q minus 1. So this is essentially M times M to power, let's say, P minus 1 to the power K times Q minus 1. Therefore, this one under modulo P by Fermat's Little theorem is congruent to 1. So under modulo P, this can be canceled out. So what you get is C to power D under modulo P is congruent to M. By the same logic, the same goes for modulo Q. So C to power D is congruent to M modulo Q. And now you have two congruences. C to power D is congruent to M modulo P and also congruent to M modulo Q. And therefore, it's clear that since P and Q are prime numbers, they are obviously co-prime. These two congruences yield C to power D is congruent to M modulo PQ. Well, P times Q is N. So what does this mean? If you know the multiplicative inverse of E in modulo N, you can simply decrypt the message by taking the power C to power D modulo N. Okay, so that is the way to decrypt. You have to compute the multiplicative inverse of E under modulo n, and then raise c to power d under modulo n. Let's see this on an example. Decrypt this message 09810461, where n is given as 2537, e is 13, the same public key we have seen in the earlier example. P and Q are these values. Now P minus 1, Q minus 1 is 42 times 58, 2436, and 937 turns out to be the multiplicative inverse of 13e under modulo 2436. Therefore, that we choose as D. And simply to decrypt your message, again, since we are using blocks of 2, remember the earlier example, we take the first block as 0981 and raise it to power 937 under modulo n. You get 0704. And the second block, 0461 raised to power 937. Well, 0461 is simply the number 461. Okay, this is not a different encoding, it's just a decimal number raised to power 937, and take modulo n, you get 1115. So when you decode this, 07 corresponds to H, 04 corresponds to E, because that's the fifth letter. 11 is L, and 15 is P. So the message is help. Now, it looks like we have decrypted this quite easily. So what is the point of this? The point here is you announce N and E, but obviously you do not announce P and Q, and obviously not D. So some other third party only knows the N value and the E value. What you need to decrypt is D, the multiplicative inverse of E under modulo N. But for that, you need the number N to be factored out to be able to compute this multiplicative inverse. But the numbers P and Q are not announced. So here we were readily given the values P and Q. So we were able to compute, sorry, I have to correct something I said earlier. You need to compute the multiplicative of inverse of E under modulo P minus 1, Q minus 1. This value here. So you do not know the values P and Q that are not announced. Therefore, if you want to decrypt this, you have to compute P and Q by factoring out the number N. Typically, in practical applications, obviously this is not a number like 2,500, etc. It's a huge number, and the standards describe how large this number should be, so that factoring it out is not really easy. And in practice, you choose the numbers P and Q close to each other, so that the factoring of the number N is even harder. Okay, so that is the heart of the power of RSA. The number N is a very large number, which is the product of two primes, which you do not announce. But for decryption, you need those numbers because you need the multiplicative inverse of E under modulo P minus 1, Q minus 1. Since you do not know the numbers P and Q, this is not an easy task to do, because integer factorization, as I mentioned earlier, is a hard problem. In a general sense, we do not have an efficient algorithm to compute the prime factors of any given integer. Therefore, if you pick the numbers N and E carefully, then the decryption is going to be practically impossible.